So now we're going to talk about the very important p-series. And we want to find for what values of p does the p-series converge. All right, so I need to break this down into cases. All right, so now the first case I want to look at is if p is negative or 0, right? There's a pretty easy thing. If p is negative, right, then this 1 over n to the p just becomes n to a positive number, right? Because it sort of flips to the top. So let's call this case 1. I'm going to write it up here. Oops. Get my pen going. So case 1, I'm going to look at the case for where p is greater than or equal to 0. Now, obviously, if it is 0, then it just becomes n to the 0, which is 1, so it's 1 over 1, so we're just adding up a bunch of 1s. So obviously that diverges. But if p is negative, right, then because this n to the p is in the denominator, then essentially the n to the p kind of flips up to the top. So let me write that down. So then the limit as n goes to infinity of 1 over n to the p is the same thing as the limit as n goes to infinity. I see I left off the infinity here. Of n to the negative p, right? And if p is negative, then we're talking about the negative of a negative, so it's n to a positive power. And n to a positive power as n goes to infinity is never going to be equal to 0, right? So that's our test for divergence. So in this case, the series diverges by the test for divergence. Let me write that down. So the series diverges by the test for divergence. Okay, so that's case 1. Now case 2, I'm actually going to break into 2 subcases, okay? Because basically I'm looking case 2, I'll just write it off to the side here. Case 2 is essentially for p greater than 0. Okay, but we've got a special case in there because essentially then it's essentially a power function, right? With a negative power. If p is greater than 0, we can always make it, n to the negative p, and so then it's just a power function except for the case where p is equal to 1. So that's why I'm going to break it up into 2 subcases. So case 2a, I'll call it, is if p is equal to 1, right? And so then we have the harmonic series, right? So then we have the harmonic series. And if you watched the video, for example 1, we looked at the harmonic series and we found that it diverges. So we know, which we know diverges. Okay, so if you look at example 1, you'll see why. We applied the integral test to that example 1, and found that it diverges. Okay, so now to case 2b. Oops, let me see here. Case 2b is going to be the rest of the cases for p greater than 0, but p is not equal to 1. Okay, so then and then we have the function 1 over x to the p, right, which is continuous, positive, and decreasing, right? Which is continuous, a lot of words here, continuous, positive, and decreasing. on 1 to infinity. So we can apply the integral test, right? So we can apply the integral test. All right, so let's do that. So we're going to integrate this. I want to integrate from 1 to infinity, right? So, but I'm going to integrate from 1 to t. And I'm integrating 1 over x to the p, which is the same thing as x to the minus p dx. It's just a little easier to work with it that way. So when I integrate that, I'm just going to add 1 to the exponent, so it becomes negative p plus 1 over negative p plus 1, right? And then I want to evaluate that from 1 to t. And what I end up with is, now I have this negative p over 1, or sorry, yeah, this 1 over negative p plus 1 in the denominator, I can bring that out. So that's just a constant. So I'm gonna bring that out front, and then I can evaluate the x to the negative p plus 1 at t. So that's t to the negative p plus 1. And then I can evaluate the same thing at 1. So 1 to the negative p plus 1, doesn't matter what p is, it's just going to be 1. Okay, so that's what I get when I integrate to t, but I really want to integrate from 1 to infinity of this x to the negative p dx. So that's going to be the limit as t goes to infinity of the result that I just got, right? So I'm going to take the limit of, so I have okay, yeah, if I flip that around, it's 1 minus p, and then I have t to the, I can rewrite this as 1 minus p minus 1. Okay, and so it's all going to depend on what p is, right? So if this 1 minus p is less than 0, right, then I essentially have, p is a positive number. If it's less than if this 1 minus p is less than 0, then so let me write that down. So if 1 minus p is less than 0, which means that I can rearrange this as p greater than 1, right? And so then I just get a result of 1 over 1 minus p times minus 1, right? If I just plug in, if t is, sorry, if p is 1 minus p is less than 0, then this t term goes to 0 as t goes to infinity, right? And so I get that result. And if p is not greater than 1, then it diverges, right? Because this is going to be t to some positive power, and that would diverge. But if it's t to some negative power, then I'm good. So the conclusion is that the series, the p series, so we'll call it the p series, it converges if p is greater than 1, and otherwise it diverges. All right, so that result, I'll put a little box around it because it's important, right? And that's my final answer. But it's important enough. I've got a box of its own that I'm going to write it in. So this is something that you're going to want to remember. So if we have the p series, which is the sum from 1 to infinity of 1 over n to the p, this converges if p is greater than 1, and otherwise it diverges. So that's p less than or equal to 1. All right, so there you go. We have another series that we can use for that we'll see here in the next video. I'll show you how we can use that p series in order to determine if other series converge.